Hello everyone, so today we're doing Leetcode 169 majority element. The problem says, given an array nums of size n, return the majority element. The majority element is the element that appears more than n divided by 2 times. You may assume that the majority element always exists in the array. In example 1, we have 3, 2, 3, and the majority is 3 because 3 appears 2 times and 2 appears 1 time. In example 2, we have 4 2's and 3 1's, so we return 2 because that's the majority element. Because 2 appears 4 times and 1 appears 3 times. So how can we actually solve this problem? To solve this problem, we can actually use a hash map. And that's the most intuitive way of thinking when you first look at this problem. So let's first start off with this example 1. So we're going to have a hash map. So a hash map has key value pairs. What would our key value pairs be though? Our key would definitely be the elements that appear in here, which is 3 and 2. And our value would be our frequency. So 3 shows up 2 times and 2 shows up 1 time. Now that we have our hash map, what can we do with this hash map? Well, if we look at the problem, it says the majority element is the element that appears more than n divided by 2 times. So if we use this information, we can have a variable called majority element and equal that to the length of nums divided by 2, right? Majority element. There we go. So let's say we have this scenario. So we have a length of 1, 2, 3. So 3 divided by 2 is 1.5, right? But we're using floor division. So with floor division, that equals 1. We round down. So are any of these key value pairs greater than 1? We see that there's only one scenario where there's 2. So we return that value, which is 3. So we're going to return I. And that would be 3 in this scenario. Right? Now, what is the time complexity? The time complexity would be O of n. And the space complexity will also be O of n because we have to store every value into our hash map. So we need extra memory. However, is there a way where we can solve this even more efficient? The problem has a follow-up where it says, could you solve this problem in linear time and in O of 1 space, so constant space? There actually is one method. If you look up this algorithm called Borer-Moore voting algorithm, it says the Borer-Moore majority vote algorithm is an algorithm for finding the majority of a sequence of elements using linear time and a constant number of words in memory. And this satisfies the follow-up. And the problem description matches exactly what we're trying to do. So it's finding the majority of a sequence of elements. So yeah, let's apply the Borer-Moore algorithm onto this. So let's use the same test case as earlier, 3, 2, 3. With the Borer-Moore algorithm, we're going to have 2 variables, a count. We're going to have a count. Let's put the count right here. And a candidate. And the count will initially be 0. And the candidate will be nothing, so none. So if you come with a scenario where the count is 0, we just make the candidate equal to the current index's value. So we're going to run a for loop through this list, obviously. So let's say we're at this scenario. The count is currently 0, right? So the candidate equals I, which is 3. And the count will be incremented to 1. So next, what if we're at this iteration? We see that the candidate and I aren't the same value. So we see candidate does not equal to I. So what do we do when we hit this scenario? We actually decrement the count. So when we decrement the count will be 0, but the candidate will remain 3. Right? So how about this scenario? Where the candidate and the candidate and I are the same value. So the candidate is 3 and I is currently 3. We actually increment the count, and we saw that the count is 0 in this scenario. So we still replace the candidate, right? with the current I. But in this scenario, it's the same value, so it will be 3, and the count will be 1. And at the end, all we have to do is just return the count, return the candidate, sorry. And that will be 3. And yeah, that's how you solve this problem in all of n time complexity and all of 1 space. So this is time, and this is space. And this problem is very efficient, and it solves the follow-up question that it has. So let's try implementing both ways though. So like I said, initially, if we were to implement the hash map way, we're gonna have a hash map, and we'll call it count. And initially, it's empty. So if we run a for loop through the list, so what if so currently it's empty. How can we throw items in here? So how can we throw 3 in there? So if I is not equal to I, if I is not in a count, right? So if I is not in count, we actually want to equal this to 1. So we need a scenario where this equals 1, right? So count of I equals 1. And what if we're at this scenario where it's 2? It will be 2, 1. And what if we're at this scenario? Well, this is already in the hash map, so what do? We actually want to increment this to 2, right? To increment that to 2, we'll just have an else statement where I is in the count. So count of I plus equal 1, right? So that satisfies the hash map. So now what can we do with the hash map? We said we're going to make a variable called majority element. And we'll make it up here. And that equals to the length of nums divided by 2. Right. So now we're going to go inside the for loop, and we're going to make an if statement. So if count of I is greater than majority element, you can just return I. And let's run it. And let's see if it works. And yes, it works. We don't have to return none out here because you can assume that the majority element always exists in the array. And let's see if it submits. And yes, it works. However, like I said, the time complexity and space complexity are both linear. We want to try to solve the follow-up where we make the time and space, where the time is O of n and the space is constant O of 1. So let's start implementing Moore's algorithm. So we said we're going to have a count equal to 0 and a candidate equal to none. Right? So that's what we did right here. And we're going to run a for loop through the list. So for I and nums, what do? We saw if the count is 0, we actually equal the candidate to I, and we increment the count to 1. So if count is 0, we will do candidate equal to I and count equal to 1. Else what if the candidate does not equal I? We said we will decrement the count, right? We'll decrement it. So that's where the count was 0 in this scenario. And where the candidate was 3 and I was 2, so we decrement the count. So elif candidate does not equal to I, count minus equal 1. And what if we have a scenario where the candidate equals I? So if we hit this scenario, we see that the candidate was 3 and I was 3. So what do? We increment the count, and at the end, we can just return the candidate, just like we did here. And if we submit, this should work, hopefully, if I didn't type anything incorrectly. And yes, it does. So this successfully solves the follow-up question. It has a linear time in time, and it's constant in space. So yeah, if you guys enjoyed this video, please subscribe for more. Thank you very much, guys.